In this video, we're going to review some of the exam problems from the 2017 exam. We're going to start with question number 2 in the multiple choice. We're asked to consider a surface defined by z equals x squared plus 1 sine y plus xy squared. And the question is, which of the following planes produces a parabola? Key thing, parabola here, when it intersects this surface. If you take a look at the options here, this is a perfect scenario for substituting in a value and seeing what happens. When x equals 0, what's going to happen is we're going to remove x from all the equations, and we're going to have a relationship simply between z and y. If we do that here, we're going to get 1 times sine of y plus 0, and so that's simply a sine y function. That is definitely not going to be a parabola. So we can rule that out. If we sub y equals 0 into this, let's use a different color so we can see the two contrasting examples. We would have z equals x squared plus 1 remains. Then we have sine of y, but sine of y in this case would become sine of 0 plus 0. And that altogether comes in to be just 0 plus 0. That's 0. That is also not going to be a parabola. Last but not least, we can try z equals 0. But that certainly seems like it's going to be a complicated relationship. We're going to end up with 0 equals x squared plus 1 sine of y plus xy squared. Again, with all those different values in there, especially the sine y combined with the x squareds, that also does not look like it's going to give us a parabola. For this particular problem, we essentially had to go through those options before we could arrive at the none of the above answer here. Fortunately, the work is fairly straightforward. It's literally subbing in this value and then seeing what kind of function you get back and asking whether the function you get defines a parabola or not. The next question up is question number 3. An airplane is flying at an airspeed of 400 kilometers per hour, pushed by a wind that is blowing at 50 kilometers from the southwest. So key information here: the speed of the plane, the speed of the wind, and the direction of the wind. And the plane wants to orient itself so it is flying due east. What will the airplane's speed be relative to the ground? A quick sketch helps us with this. We know one of the vectors completely, one of the velocity vectors. 50 kilometers from the southwest means towards the northeast. And so we're going to have that as our wind. And it has a magnitude of 50. I'll just tidy that up here. And then what we want is to add the plane to achieve a goal that is the net speed being due east, but the plane is going to have to fly in some element south to make this work. What we can tell simply from the arrangements here is that by going a vector of 50 here is going to have a mostly horizontal component, or a large horizontal component. This 400 kilometers per hour is also going to have a large horizontal or east component. We're definitely talking about more than 400. We can also do a quick ballpark. It's probably not going to be 450 or more by the time we get the components of this. So we're narrowing our gap or our solution down to B and C. Unfortunately, to get more precise than that, we really do need to do the full diagram here. If we imagine an angle theta here, it's the same as the angle inside this triangle here, and we look for the components that we know. The key information for the wind is that it's coming from the southwest or to the northeast, and that means that it's 45 degrees by convention. Halfway between south and west is 45 degrees. What that means is we can add the ingredients for a little triangle on the side here, and if you think back to our special triangles, there's the 1, 1, root 2, or dividing everything here by root 2. We have 1 over root 2, 1 over root 2, and 1. Or if you like, the cosine sine of 45 degrees are 1 over root 2. There's lots of ways to get the height here. 50 over root 2, though, is a key ingredient that we need here. That vertical component is what the plane has to fight, and so we know that the plane, even though it's going 400 kilometers an hour, is not doing that due east. It has to go a bit south to counterbalance the 50 root 2 here. So we have a nice triangle arrangement, and it satisfies, we make this theta a little tidier looking. We have the opposite over hypotenuse, that'd be sine. Sine of theta will be 50 over root 2 over 400. And so we can get our angle, which is about 5.7 degrees. Now that's not the answer we're looking for. Some other earlier question models have had that. What we really need to know here is the entire length of this net vector. We know part of it already. It's also 50 over root 2. This part here, though, the right-hand longer segment, is going to be related to 400 and cos theta. We're going to have cos theta equals this length, let's call it L, over 400, or that length is going to be 400 cos of 5.07 degrees. One of the rare times where we can use degrees rather than radians in a calculus class, and that gives us a surprisingly high 398.4 kilometers per hour. And if we take those two numbers together, the 50 root 2 over root 2 plus the 398.4, we end up with a grand total of 433.8 kilometers per hour. And that puts us into the second category here. So the final answer would be B. Our next question up by the poll is question number 6. So for what values are the vectors shown here parallel? What we need there immediately is a test for parallel. And the test is that, let's call this vector 1 and call this vector vector 2. If they're parallel, then v1 is equal to v2, but not actually equal, proportional to or equal to a constant times. So that's a scaled value or a scalar multiple of the other vector. And so what that means is we can set up equations that the components have to match the same equation. 6 would have to equal k times 2, 4 would have to equal k times that entire expression there with all the fractions and such, and last but not least, negative 3 would have to equal k times t. From these equations, we quickly get that k would equal 3. Then if we look at how we can use that in our other equations, the second equation has quadratics for t. Let's not dive into that. Let's take this and use it in the third equation. That has the advantage of giving us t very quickly, because we have k has to be 3 to satisfy the first equation. That means t has to equal negative 1 to satisfy the second, or the last, rather, the third. And then we're just going to check, if we put those two equations together, that we actually do get 4. So do we get k, which is 3, times t squared, that's 1, plus 2/3 times negative 1 plus 1. That's 2 minus 2/3. And minus 2/3. And that's actually going to be 6/3, 4/3. 3 times 4/3 is in fact 4. And that is exactly what we had on the left-hand side. So those values, t equals negative 1 and k equals 3, work. And that gives us our answer of A in this case here. Another approach shown in the solutions is simply to try each of these values. Sub t equals negative 1 in, you see that you get two parallel vectors. If you sub in the two other values of t, you find that that's not the case. And if those don't satisfy the parallel system, then you're certainly not going to have it true for all real values of t. In number 9, we're looking at a differential equation, and we're asked to use Euler's method to predict what's going to happen over a few time steps. The important thing to remember here is just what the method is, and it's easier to do that if you keep a graphical perspective on it. What we've been told is that we're going to start at x equals 1 and y equals negative 3. So we're going to be starting at 1, and we'll actually move our axis up. And we are at the point 1, negative 3. At that point, we can compute the slope of the graph of y against x using the differential equation. with x equals 1, y equals -3. That's going to give us a slope equal to dy dx of y plus 2x. That's going to be -3 plus 2 times 1, and that's going to be -1. So we can build a slope value in there if -1 or if 45 degree down. We can then use that slope with the delta x they gave us of 0.5. And we can predict that we're going down by 0.5 to follow that slope line, rise over run. Or you can use the equation, the change in y is going to equal the slope times the change in x. That's Euler's method. All we're doing is taking, as a reminder, delta y over delta x is slope. We bring this delta x up to here, and we're just rearranging it to solve for the thing that we want, given the things that we know. We know the slope in delta x. So we have -1 times 0.5, and so we get that same -0.5 value. So when we take that step, we started at x equals 1, we add 0.5 to that. We also started at -3 for y, we went down by that, so our new y is our old y plus the delta y, and that's -3 minus 0.5. -3.5, and that makes B our final answer for that problem.